Good afternoon, everyone. My name is Johan Arendt, and today I will present interpretable artificial intelligence to identify biases and build trust with end users, an application to SONAR seabed characterization. So first of all, I will introduce you to deep neural networks, the different qualities and errors of deep neural networks that you want for your application, and then different interpretability methods that we've built for the application to the SONAR seabed segmentation. And then I will conclude with the active learning and building trust with the end users. So first of all, deep neural networks are a generic optimization process that are composed of simple mathematical operations at the cell or neuron level. This is weighted combinations of the inputs with an addition of a bias vector and or an activation function. This is graph-based optimization methods that is supervised and driven by the data. For example, you can have different types of tasks from regression, where you try to predict the housing price of a neighborhood, or binary classification where you try to decipher one image from being a cat or a dog. The first type of neural networks is the artificial neural networks, for which you can see a graph on the left, which is a fully connected graph, and which is given expert features at the input level, which can be any transformation of the input data, given proxy detectors such as the eye nose detector, for which you can craft the eye nose width ratio feature, which is here in red on the left. And then the model for binary classification will outputs probability score of the image being a cat. Here it's the 0.998. The second type of architecture has been introduced because the researchers were wanting to go wider and deeper with the models, working then with bigger data in the input, such as the MNIST digits, where you can see an example on the bottom right. The idea was to craft the feature extractor by learning the different features inside the neural networks optimization process, and the convolutional neural network type of architecture was the best performing thanks to its spatial convolutions, which works locally. This is where you can see on the bottom the convolutional neural network filters and associated feature maps on the bottom left. And you can see the flow of and then those convolutions were fed to subsampling operations, reducing the size of the feature maps before feeding everything into a fully connected network. This is the graph of this is the diagram of LeNet 5 on the right, on the top right. Fully connected layers that forms the binary or multi-class classifiers that we've seen on the previous slides. Then let me introduce you to different qualities and errors of deep neural networks, because the idea of those architectures are to get emergence from the complicated combination of everything. And then to get desirable properties. So we are working from the input data, sampling data points from the input manifold. This is the graph, the diagram on the left, where you have those points. We also have in this computation the type of architecture, the way you organize your model, the training procedure, the way you organize this training procedure, and regularization, if you had regularizations. And all this crafts big black boxes models that are difficult to understand or to explain. You also have to take into account this kind of model alignment where we give humans gives goals to the machine by translating human goals into mathematical formulas, but for which with those black boxes you get no guarantees or few guarantees of convergence, goodness of fit, generalization, ability, etc., etc. So on the left you have this diagram of input data features of a toy example of binary classification. So first of all, the first sorry, the first error that you can face with your model is overfitting, which is the learning procedure becoming too close to the input data, to a loss of generalization ability of the model. This is the decision boundary that you can see on this overfitting of this continuous boundary overfitting on the left. Possible solutions include data augmentation, different loss functions, different types of regularization, either bigger or different architecture, or even dropout. And you can also find types of overfitting with discontinuous boundaries. Here it's the black circle around the blue cross. Before we continue on the different types of errors of of the whole training procedures with the model and input and of data and input data, we can find I would like to explain the dropout, which can mitigate the overfitting. So during the training phase, you randomly discard some activation with the given probability, and you do that at every step. This prevents the model from relying too much on the hold weights. This implies also longer training, but fortunately redundant activations for a better generalization ability. And at the inference phase, you have to rescale the activation by this probability factor that you introduced to get the same range of linear combination of activations. So on the left you have one example with those red crosses of this dropout technique. So next we have another error that can arise from the training procedure. Well, standard error. This is underfitting, where the convergence is halted before a satisfactory solution. This is mostly due to label noise with all the regularization in the training procedures of modern CNNs, and possible solutions include better data registration and or normalization, different loss functions, smaller or different architectures, etc. Then we can also find in the input data distribution the effect of imbalance, which is another representation of some classes over the others, which can alter the decision boundary and can lead either to underfitting or overfitting. Here possible solutions are to repeat samples of underrepresented patterns or classes, or weight the loss per class counts. And you have this diagram illustrating the time balance on the left with fewer blue crosses. I would also like to introduce the confidence of neural networks and also uncertainty. We can simply define the uncertain area around the decision boundary. This is the gray part with a threshold around this zero point 0.5 score. And in binary classification, we have a kind of analogy between the score and the confidence. And around this uncertain area, we shouldn't trust the predictions of the model. But the problem is some models become overconfident. This is the effect of this reduced uncertain area, compressed, where the confidence is compressed around the decision boundary. This is mostly due to the exponentiation in the loss functions and also fitting art labels. So the 0 or 1 for the cats and dogs. And so this is an example of overconfidence that we would like to avoid. Last but not least, I also want to introduce you to the out of distribution. In the out of distribution, we're looking at data outside the training and testing set. We have no guarantees of the generalization ability. Will it be smooth or continuous, or will it be terrible like this one? And possible solutions includes uncertainty estimation, confidence calibration, or other types of out of distribution detection algorithms. So we move now to the introduction to synthetic aperture sonar for mind countermeasures, for which you have an example of synthetic aperture sonar intensity on the left. You have boundaries between the sand. You have boundaries between sand waves and sand ripples, and you can see different types of noises and errors, such as motion estimation, speckle noise, etc., etc. This is mostly used in the mind countermeasures for automatic target recognition, but the problem is performance drops in a difficult environment such as rocks, sand waves, or Posidonia, which is a type of seagrass, mostly due to the fact that they cast shadows that might hide targets. And this is why we need automatic seafloor characterization by semantic segmentation for better automatic target recognition interpretability by predicting the performances of those algorithms, but also for mission planning. So moving towards interpretability, but this time for the seabed segmentation, seabed semantic segmentation. So we have our deterministic CNN model, and it will perform for each pixel, it will yield for each pixel a probability score for each class of the outputs, for which we can define the prediction as the index of the maximum probability score, but also the confidence of this multi-class classification as the maximum of the probability scores. And we can also, and then you have this predictions on the left. This is the middle image on the left, and you can compare those to the ground truths by manually annotated by an oracle annotator. And comparing those two images, you can get the overall accuracy, which is the frequency of correct predictions compared to the manual annotations. Here we have already a nice score of 90.5% accuracy over the test set. But I would like now to enter more into the details of the deterministic CNN training and evaluation. So you have the training phase, for which you start from random weight initialization most of the time. As it is supervised learning, you train the training data, the input intensities, but also the ground truths. and you compare the ground truths to the predictions of the models. Then you backpropagate the error or the loss to all the different model parameters. And during the inference phase, you just give him the actual data, the test data or evaluation data, and then you get predictions that will be well, non-deterministic. Sorry, deterministic predictions. Will get the same results across multiple evaluations. But one of the interest of dropout is to be able to in a way estimate uncertainties. The idea is to get non-deterministic predictions by keeping dropout activated at inference time. So you keep the same training phase with the dropouts, but at the inference phase, you also keep this dropout activated. Then you will sample from crippled models that will yield multiple probability vectors and also multiple predictions. This is the diagram you can see on the left. There is another method, which is the deep ensemble. This time you take multiple models, you train multiple models with the same hyperparameters, with different random initialization of the weights, different shuffling, data shuffling, which is the order in which you present the data to the model. Both methods, Monte Carlo dropout and deep ensemble, will yield multiple probability vectors that you can average and for which you can calculate the entropy for which is then a metric of uncertainty. And this normalized uncertainty can be related to 1 minus the confidence if we want to plot everything in the same range of data. And this uncertainty is then a good calibration metrics, because you have variational interpretations, because you've been sampling different models and giving the same input data. So yeah, you have variational interpretations, and so you have guarantees by these sampling operations. This is an example of results, comparison of results between deep ensemble and the deterministic model. So first of all, I would like to reintroduce you the idea around boosting, which is the combination of multiple predictions. You can do it by averaging, as we've seen before with this Monte Carlo dropout method or deep ensemble, but you can also add another layer of neural networks to distinguish between the different models. Here we have a performance increase of the deep ensemble averaging for boosting up to 92.8% overall accuracy of the test set. But we also have a better uncertainty estimation in the term of better error being penalized around the misclassification. The deep ensemble uncertainty estimation penalizes either the errors and misclassification. This is the light blue that you can see in the bottom left image, the confidence map of the deep ensemble uncertainty. Well, and it has also another interesting effect of penalizing underrepresented patterns in the input data distribution or in the training datasets. This is the yellow-orange part of the bottom left image, which is which corresponds to spots of growing Posidonia, which is not represented well in the input data distribution, showing the model hesitating to classify correctly it. But you can also want to quantitatively evaluate the calibration or the uncertainty, these uncertainty estimators, by calculating the average overall accuracy per bins of confidence. You want to correlate that to the ideal calibration. When the models predicts perfectly its own errors, then it's the straight line green, sorry, not green, black curve, for which under it will be a case of a model being overconfident. I also included there the weird distribution of the confidence and and accuracy, only confidences, counting them in seabed segmentation. And this accounts for the artifacts due to the few samples below 0.3 confidence score. We can see from the calibration curves on the top right that Monte Carlo dropout combined with deep ensemble entropy performs best at finding at uncertainty estimation. It is closer to the ideal calibration compared to the deterministic CNN in blue, and also being slightly underconfident, which is more interesting because this way we err on the side of caution. We can also use this Monte Carlo dropout by looking at the distribution, probability distribution. There, the predictions over the whole test sets are plotted. First, there is the deterministic model, which has a lower overall accuracy. And you also have the probability distributions from all the cripple models, but you can also compare that to the standard Monte Carlo dropout average probability distribution with 30 crippled models. This deterministic inference between being quite lower than the predictions of all others crippled models show that the deterministic model is overfitting, but the curves we get indicates all other types of problems with the models, because the boosting in green didn't improve the expectation over the overall accuracy compared to the probability distribution of the crippled models in blue. But we can also use this Monte Carlo dropout for other interpretability methods. The idea here is to use to perform outliers detection. For each image in the test set, we are looking at the different overall accuracy for each Monte Carlo dropout predictions. If one prediction is falling below a low accuracy threshold, then we can decide that it is an outlier detected by these methods, because the Monte Carlo dropout is not performing consistently. This gives us insights into the input data distribution at training. This is what you can see with those two columns of images, left and right. On the left, you have from the manual notation sand ripples and rocks, and the two different runs of Monte Carlo dropouts shows you the bias towards rocks during the manual notation that the annotator choose to do in the training set, with the bottom left image, the G1, being overflowed by rocks outputs. But on the right, you also get a nice example of subset adaptation, where the disjoint classes of the different subsets, here the different mission campaign at sea, are different. Therefore, the different subsets, you get different disjoint subsets of possible classes, and the model being able to maximize its performances by learning two modes between the two surveys at the cost of loss of generalization ability. And this Monte Carlo dropout recovered that by showing us the different that the model is unable to distinguish between flat sediments and sand ripples. Last but not least, I would like to introduce you to another method that is quite interesting for interpretability, the saliency maps. The goal here is to interpret the pixels that contribute most to the final decision. You first choose a target layer. You expect it to be deep enough to hold insights about the classification. Then you project the loss function. Remember the prediction versus the ground truth on the query class. Here it would be from the output vector on the right, the send ripple class, because the model thinks that the input image is mostly composed of send ripples. Then you look at the combination of backpropagated gradients from the loss function at all feature maps of the target layer, and then this is the image on the right in green, on light green, light blue, cyan, everything you want, name it. You get this by normalizing the map between 0 and 1 to take into account the varying contributions of the different classes with respect to the loss. And here in the saliency map explanation, you can see the places where the model is taking its final decision to tell that the image is made of sand ripples. But you can also use you can also use this saliency maps with other types of neural networks. So first of all, let me introduce you to the misclassification masks that you can compute from the binary difference between the ground truths, the top image, and the predictions, the bottom image. Then intersecting that with the ground truth image gives you misclassification per class, and you can perform blob detection to get misclassification mask with the same class associated to the whole mask. And you can use that as a query for semantic segmentation saliency map. So here it's an example of a saliency saliency map applied to a semantic segmentation model, which will yield one output vector per pixel. This is the output segmentation map, the colored on the colored image on the right. So the idea is the same, to interpret the pixels that contribute most to the final decision, but this time given the misclassification masks. So at the target layer, you will backpropagate the loss, but this time you will not only project it on the query class, but also mask it out to the pixels of interest before applying the backpropagation, which will give you the saliency map, and you will have a better understanding of it with this close-ups, with those close-ups. So it helps us understand the misclassifications or annotation errors. Here, this misclassification mask generated by the ground truth and the predictions of the model show reliable sand ripple predictions at the mask, and indicating that it was an annotation error in the ground truth, because the saliency close-up is very close because the saliency explanation is very close to the query mask, and there are no pixels activated from the rest of the image that would be expected in a misclassification example. So finally, I would like to conclude with the active learning. But first of all, let's talk about these uncertainty estimation methods that gives us nice confidence maps. First, you can automatically generate confidence from from this high confidence maps, you can generate labels from these predictions. This is the group of images on the right, the confidence map and associated generated labels. The idea here is to select the top confidence, so the least uncertain images, and you can then also reject the uncertain images. This is the green, blue, lower confidence in the confidence map that got rejected on the close-up at the bottom of the slide, and you can import them automatically into the annotation software, which is what we want for this kind of active learning method. Active learning tries to find the most valuable images to annotate from the unlabeled pool of images, all the rest that you've been acquiring through all different surveys. The idea here is to make the most out of the annotation time of oracles, which are human annotators. Then you can make good use of this uncertainty metric derived from Monte Carlo dropout or deep ensemble. You can also use a diversity metric to deal with imbalance and reduce the amount of images being annotated. And you do that by the other way around, bottom ranking the confidence scores, which are summing the confidence map scores per pixels. You then select the top the most uncertain images. Here you have an example of this low confidence map, high uncertainty image and associated manual annotation, re-annotation from the annotator, showing that shells were present in the image but not in the input data distribution, and showing that this method effectively detect uncertainty estimation effectively detect those underrepresented patterns or not represented patterns. You can also perform this selection per diversity group to reduce then the number of images seen by the oracle, and you keep iterating until the criterion or budget is reached by retraining the model and recomputing the confidence maps. This is the diagram of the active learning loop that you can see on the bottom of the slide. And then all of this help us build trust with the end users by implicating them in the learning process so that they have a better understanding of the model. We give them tools to understand the results of the model with the outlier detection, indicating the cases where the model is bound to fail. Also biases identification, such as overfitting detection. But we also give them trustworthy and calibrated confidence maps that assess the performance of the model. But we can also give them other tools, such as the automatic annotations or the active learning to help them annotate the difficult cases and to implicate them more into the learning process by iteratively watching and contributing to the learning and to the performance of the model. So much for my presentation. So my name was Johan Arendt. I was working on this project at the Royal Military Academy with Professor Xavier Nate and Dr. Olga Lopera-Tellez. And now I will be glad to hear questions for you and answer your questions.